We're looking at exponential models, and in this portion of the lesson I want to do a couple of examples where we determine the algebraic model or the equation given either a graph of an exponential growth or decay, and then a second type of problem where we determine the algebraic model or equation when we're given 2 points that are on the graph of an algebraic or of an exponential growth or decay. Now, in order to do that, we need to understand that when we're asked to write an algebraic model of an exponential growth or decay, we need to bring to mind that the equation for that model is going to be y equals a times b to the x. And our job is going to be to determine the value of a and the value of b. And in order to do that, we need to know what those letters represent. And we talked about those in a previous lesson, so we're not going to spend a lot of time doing that here. A, you remember, represents the initial population or the initial value of the function. And as we talked about in the other video, that value can be determined by finding where the x value is 0. So when x is 0 and 0 is substituted into this expression, because anything to the 0 power is 1, this b to the x portion of the equation becomes a 1, so you have 1 times a, and that's where a can be found. So when we're looking at a graph, we want to look at where x is 0, and that will give us the value of a that goes into the equation. The value of b, remember, is the growth factor. Now the growth factor is determined by adding 1 to the growth percent. So when we're looking at a graph, we're going to have to figure out what the percent decay or growth is. And a quick reminder of the arithmetic of percent, the percent is equal to, that should be equal to, the difference between two values divided by the initial value. So we're going to need to determine the difference between two values from the graph and then divide that by the initial. That will give us the growth or decay percent. Then remember, that's not the number that goes in to the equation, because what goes into the equation is 1 plus that percent, whatever that may be. Alright, so let's take a look at an example or two. So in our first example here, we have the graph of a exponential decay. I know it's a decay because I can see that the values are going down as we move from left to right. So this is a decay, so that tells me my b value should be between 0 and 1. So we'll keep that in mind moving forward. To determine the initial value, you remember that that is when the x value is 0. So on my graph, I find the x is 0, and I go up, and when x is 0, the y value is 12,000. So my a value here is going to be 12,000. That's the initial population or initial amount of whatever it is we're talking about here. Now, in order to find the decay percent, I'll need to subtract the two y values here and then divide by the original one or the larger one here. So I have a y value of 12,000, so if I take 12,000, I don't know why I put a comma there, minus this y value I see right here that they have labeled for me is 1,200. So if I take that and then I divide it by 12,000, that's going to give me my decay percent. When I do that, I get a percent of 0.9, or that would be 90% if I changed it. Now I want to leave it as a decimal. This 0.9 is not what goes in for b, because remember, b is not the growth percent, it is the growth factor, which I determine by adding 1 to this value. Now this is a decay, so this is going to be a negative 0.9. Things are decaying at 90%. So 1 plus a negative 0.9, or more simply put, 1 minus 0.9 gives me a 0.1, so my b value is 0.1. So I now have my a value, I have my b value, so I simply substitute it into the exponential equation. So I have y equals 12,000 times 0.1 to the x power. This is the algebraic model that represents this graphical model of this exponential decay. The second type of problem that we'll do here is that we need to write an exponential function that includes the given points. In other words, the exponential growth or decay model goes through these 2 points on the graph. And so we need to figure out the equation that when I put in this 4, it produces 8, and when I put in this 6, it produces 32. Now this is really just a matter of using the substitution method that we use with linear equations. In other words, let me go to another flip chart here and I'll show you. Let's see. Remember 4, 8, 6, 32. All right, 4, 8, 6, 32. 4, 8, 6, 32. 4, 8, and then 6 and 32. So I have 2 points that I know come from the equation y equals a times b to the x. So this is an x value and this is the y value. This is the x value and this is a y value. So I know both of them come from that equation, so I can substitute those in. So y is 8, and then I have a times b when x is 4. Okay, that's simply substituting in y and x. And then substituting in y and x here, I have 32 is equal to a times b to the 6th. And what I have here is simply a system of equations. And you remember from linear equations that to solve a system of equations, I use substitution or elimination. So in this case, I want to use substitution. So I need to solve one of these 2 equations for a or b, then substitute that into the other equation and find out what that value is. So I'm going to choose and take this first equation and solve it for a. So solving for a, I'm going to divide both sides by b to the 4th. So a is equal to 8 divided by b to the 4th. That's simply an algebraic manipulation of this. Now that I know what a is, I can substitute this into the other equation and then solve. So substituting into the other equation, I have 32 is equal to a, which I have from this other equation as 8 over b to the 4th times b to the 6th. And now I simply do a little bit of algebra. So 32 is equal to, and then I'm going to write this out as 8b to the 6th over b to the 4th. And that's simply, multiplying this numerator times numerator, denominator times denominator, multiplying fractions. Now, you remember from what we did earlier, because I have the same variable here, I can reduce these. So I have 4 b's in my denominator, reduces with these 4 b's, leaving me b squared. So I have 8b squared over 1. Then dividing by 8, I have 4 is equal to b squared. Taking the square root, I have b is equal to plus or minus 2. Now, we're only going to use the positive 2 here. We'll use the principal square root. So now that I know what b is, I can now substitute this back into this equation that I have here in order to figure out a. So a is going to be equal to 8 over b, which I now know is 2, to the 4th power. So a is equal to 8 over 2 times 2 is 4, times 2 is 8, times 2 is 16. So a is equal to 1/2. So I have my a value, I have my b value. So the algebraic model then that represents this is y equals the a value, which is 1/2, times b to the x. This is my algebraic model that contains these 2 points. So finding the algebraic model when you're given 2 points is simply applying what we already know how to do using substitution that we learned way back in Algebra 1. Substitute in each of these values and then use the substitution method to solve for the missing variables. If you'd like, I'm going to do one more of these just so you can watch another one being done. If you think you have it, then go ahead and tackle your homework. So again, I'm given 2 points. I know that they come from an exponential model. I simply need to figure out what that exponential model is. And again, whenever they say exponential model, what should come to mind is the equation y equals a times b to the x. Now, I know these came from this equation, so I can substitute these back in for the variables from which they represent, and then I can use substitution to solve for the ones that are missing. So I have a y value of 24 that is equal to a times b, and then this is to the negative 3 power. That's one equation. And then I have a y value of 12 that is equal to a times b, and then I have to the negative 2 power. So again, I have a system of equations here that I can now use substitution to solve. So I'm going to choose this second equation this time and solve this equation for a. So a is going to be equal to 12 divided by b to the negative 2. Now don't be fooled here to thinking that because this is now in the denominator, the exponent becomes negative, because it's only in the denominator because I divided by b to the negative 2. I didn't simply move it to the denominator. Because this is negative, I'm going to go ahead and move it to the numerator right now where it will be positive. So my a is going to be 12 times b squared. So this is the value of a. I'm now going to substitute this into the second equation and then use that to solve for the missing variable. So I have then 24 is equal to the a value, which I now know is 12b squared, times b to the negative 3. Now, these are numbers or variables that I'm multiplying together so I can add the exponents. So I have 24 is equal to 12b to the negative 1. And then dividing by 12, I have 2 is equal to b to the negative 1. Now, in order to make this exponent positive, I need to move it to the denominator. So that's going to be 1 over b is equal to 2. And now I'm going to multiply both sides by b in order to get this, and so then I end up with b is equal to 1/2. So now that I know what b is, I can substitute it back into this equation to determine the value of a. So a is equal to 12 times b, which I now know is 1/2 squared. Now be careful here, we must do exponents first. So this is 12 times 1/2 squared, which is 1/4. Now I can reduce this, so I have an a value of 3. So now I have my a value and my b value. I can write my algebraic model. So y is equal to my a value, which is 3, times my b, which is 1/2, to the x power. So I have my relationship between y and x, and I have my a value and my b value determined given 2 points.